Welcome to the Deep Dive, the in-depth analysis you need to understand the stories shaping our world, or in this case, our entire universe. Today, we are peering into what has to be one of the most staggering cosmic mysteries out there. And I want you to just take a moment to think about this. Everything you see when you look up at the night sky, every star, every galaxy, and then think about everything you are, right? Every atom, every molecule, your very existence.
It's all just a tiny fraction. It's almost insignificant.
Mhm.
You gather up all of that ordinary luminous matter in the cosmos, what physicists call baryonic matter. You've only accounted for about 5% of everything.
5%.
Yeah.
That's the ultimate cosmic humbling, isn't it?
It really is. Everything we are, everything we can see and touch is, in the grand scheme of things, a tiny anomaly.
And that remaining 95% is completely invisible, completely enigmatic. It's split between two massive unknowns. You've got about 27% dark matter, which is this strange invisible glue holding galaxies together, and then 68% dark energy, an equally mysterious force that's actually pushing the universe apart, making it expand faster and faster.
Right. And chasing that hidden 95% is where all the revolutionary science is happening right now. I mean, when we talk about dark matter, we aren't talking about some niche fringe problem. We are talking about the central scaffolding that built the entire universe.
Scaffolding, I like that. So without it,
But
what, galaxies wouldn't form?
they wouldn't exist as we know them.
Mm-hmm.
Without the immense gravitational influence of dark matter, those large-scale structures, the organization of galaxies, the cosmic web we observe, it simply wouldn't have formed.
So the mission for this deep dive is to really unpack the whole story for you. We're going to trace the concept from the very first historical observations of missing mass almost a century ago through the revolutionary astronomical evidence that turned it into an accepted fact. And then we're diving deep into the extreme lengths scientists are going to today to try and catch this thing.
And we mean extreme. Massive detectors buried a mile underground, cutting-edge space telescopes.
Yeah.
It's an incredible hunt.
Okay, let's unpack this. How did we get definitive proof that something we can't see or touch or interact with is actually the dominant form of matter in the universe? And crucially, what are the leading candidates for this invisible particle? But before we jump into the history, we really have to clarify the term itself. When we say dark, we don't mean it's like shadowy or black, right?
Yeah, that is a crucial point, and it's where the name can be a little misleading. Dark doesn't describe a color. It means that it does not interact with the electromagnetic force at all.
So that means no light, period.
No light, it doesn't absorb, it doesn't reflect, and it doesn't emit any kind of electromagnetic radiation. Not visible light, not X-rays, not radio waves, nothing. It's completely invisible to every telescope we have ever built.
Okay, so if we can't see it with light, how in the world do we know it's there? How is it even detectable?
Through the one fundamental interaction it does participate in, gravity. It takes up space, it has mass, and we can watch that mass exert a powerful gravitational pull on everything we can see, on stars, on gas clouds, and even on light itself. Dark matter is defined almost entirely by its gravity, which warps space-time and dictates how all the visible stuff moves.
So this mystery of missing mass has been lingering for a long, long time, but the idea really got its first tangible footing, nearly a century ago, through the work of a brilliant but famously eccentric scientist whose findings were at first just completely ignored.
That's right. The story begins with Fritz Zwicky in the 1930s. He was a Swiss-born astronomer at Caltech, and yeah, a famously difficult character, but his insight was absolutely profound. He was studying a huge, dense group of galaxies called the Coma Cluster.
And what did he see in the Coma Cluster that was so shocking?
He was trying to measure its total mass, and he did this in two different ways. First, he estimated the mass of all the visible stars and the luminous gas he could see. But then, he also measured the velocities of the individual galaxies buzzing around inside the cluster. He used something called the virial theorem to basically calculate how fast everything was moving.
And there was a huge discrepancy.
A massive one. Based on the gravity generated by only the visible matter, the stars and gas, the galaxies were moving far, far too quickly. Their kinetic energy was just way too high for the gravitational pull of the luminous mass. According to Newtonian mechanics, those galaxies should have been moving fast enough to escape the cluster's gravity entirely.
So they should have just been flying apart, dissipating into space?
Exactly. The cluster shouldn't have been stable. It should have just evaporated.
No.
But it wasn't. It was stable. It was a single, gravitationally bound unit.
Okay, so Zwicky realized there had to be something else there.
Precisely. He realized there must be a huge amount of unseen mass. He estimated maybe 10 to 100 times more than the visible stuff, acting like an invisible tether, providing the extra gravity needed to hold it all together. He called this missing component Dunkel Materie,
Which is just German for dark matter.
just German for dark matter. And the response from the astronomical community at the time,
Well, weren't buying it.
not at all. It was met with huge skepticism, bordering on outright dismissal. I mean, Zwicky's estimates were a bit crude, and the whole concept of a massive invisible component was just too radical. To propose that 90% of the universe was just missing, it was a fringe idea that basically sat on a shelf for decades.
And that independent confirmation finally arrived in the 1970s, completely changing cosmology forever. And this was thanks to the persistent and crucial work of the American astronomer Vera Rubin.
Yes. Vera Rubin's work provided the undeniable, concrete evidence that the scientific community needed. She, along with her colleague Kent Ford, shifted the focus from huge galaxy clusters down to individual spiral galaxies, most famously the Andromeda Galaxy. And what they did was measure the orbital speed of stars at different distances from the galactic center. This is called a rotation curve.
Okay, so let's clearly define the expectation here, because this is the core of the problem. If you look at our solar system, the planets closer to the sun move faster, right? Earth moves faster than Jupiter, which moves faster than Neptune.
Exactly. And when you look at a spiral galaxy, almost all the visible mass, the stars and the gas, is concentrated in that bright central bulge in the inner arms. So if gravity worked based only on what you can see, you'd expect the stars way out on the edges to be moving much slower. Their velocity should drop off the further away you get.
But that is not what Vera Rubin saw at all. She found the rotation curves were flat.
Flat, which was stunning. It means that stars way out on the periphery of the galaxy, orbiting tens of thousands of light years from the center, were moving just as fast as the stars near the core. And this wasn't a one-off. This was a consistent observation across dozens of galaxies she studied.
That's the smoking gun, isn't it? If those outer stars are moving that fast, but the visible mass ends way before that, they should be flung out into space.
Centrifugal force should have ripped them right out of the galaxy. The only physical explanation was that there had to be a gigantic spherical halo of invisible mass surrounding the entire galaxy, extending far beyond the visible light. This massive unseen halo was providing the extra gravity to keep those fast-moving outer stars in orbit. And that halo is dark matter.
And her work was so systematic, so compelling, that it just rapidly shifted dark matter from Zwicky's old controversial hypothesis to a widely accepted astronomical fact. And it's important to mention her persistence, too. As a woman in science back then, she faced enormous hurdles.
Oh, absolutely. She was denied entry to graduate studies at Princeton just because they didn't accept female astronomy students at the time. Her legacy is not just the discovery, but her intellectual tenacity. She eventually became the first woman officially allowed to observe at the Palomar Observatory, which, ironically, is where Zwicky had done his work decades earlier. Her evidence just solidified it. Dark matter dominates every single galaxy.
So by the end of the 1970s, we had this compelling, widespread, circumstantial evidence based on motion. Galaxies spun too fast, clusters held together. It was the best explanation, but it was still an inference.
Right, it was still based on velocity anomalies. The scientific community needed something more direct, an observation that could prove dark matter wasn't just missing mass, but a truly distinct substance, physically separate from normal matter.
And that definitive, irrefutable proof finally arrived in the early 2000s from one of the most energetic events known since the Big Bang, the Bullet Cluster.
Here's where it gets really interesting. The Bullet Cluster, about 3.8 billion light-years away, is the aftermath of two colossal galaxy clusters colliding at incredible speed. This event was the perfect cosmic laboratory.
Why a collision? What makes that so special for this kind of test?
Well, a galaxy cluster is mostly empty space and hot gas. When two of them smash through each other, the stars themselves, the visible galaxies, they barely interact. They just pass right through one another. But the hot gas and the dark matter, they behave very differently. And that is the key.
And to see these different components, astronomers had to combine observations from multiple instruments, creating that famous composite image. We should break down how they managed to see the invisible parts.
Right. That image is actually 3 different pictures layered on top of each other. Each one reveals a different slice of the universe's mass.
Yeah.
First, you have the normal matter. This is mostly vast clouds of superheated gas, or plasma, and it contains most of the baryonic mass of the clusters. It shows up as pink in the image.
And how do we see that?
This gas is millions of degrees Celsius, so it emits powerful X-rays. That's what the Chandra X-ray Observatory detected. And when the two clusters collided, this hot gas slammed into the hot gas from the other cluster.
It's like two massive plumes of sticky smoke hitting each other.
That's a perfect analogy. The hot gas suffers immense drag and electromagnetic forces. It's slowed down dramatically and piled up right near the center of the collision. That's where you see those two distinct clumps, with one shaped like a bullet.
Then we have the visible galaxies, the stars themselves, which show up as orange and white. And those were seen by optical telescopes like Hubble and Magellan.
Yes, and as we said, those mostly just sailed right through the center because there's so much empty space between them. They didn't really slow down. Now for the final, most crucial component, the stuff that actually contains most of the total mass. In the image, this is mapped in blue. This is the distribution of the total mass, and it's determined without using light at all. It uses gravitational lensing.
Gravitational lensing. This is such a powerful idea. Can you explain how invisible mass can reveal itself just by bending light?
Think of space-time as a stretched rubber sheet. Any object with mass, a star, a galaxy, or a cloud of dark matter, creates a dip in that sheet. Light from a distant galaxy that travels across the universe has to follow the curves in that sheet. So when that light passes near a massive object, it gets bent and magnified, creating distorted, stretched-out images of the background galaxy.
So by looking at how stretched out those background galaxies are, you can map where the gravity is strongest.
Precisely. You can meticulously map out exactly where the total mass must be concentrated, whether that mass emits a single photon or not. And that's how they produce the blue map.
Okay, so here's the moment of truth. When they overlaid the blue map of total mass with the pink map of the normal gas, they found they were in two different places.
That separation is the absolute proof. The pink stuff, the normal matter, the gas piled up in the middle because of drag. But the blue stuff, the dark matter, which is where most of the mass is, it just kept going. It sailed right through the collision without slowing down, moving ahead of the gas.
It's proof that dark matter does not interact with itself or with normal matter in any way other than gravity.
This completely rules out the main alternative theories of gravity, like modified Newtonian dynamics, or MOND. Those theories try to explain away dark matter by saying gravity itself works differently on large scales, often linking the missing mass effect to the hot gas. The bullet cluster shows, beyond a shadow of a doubt, that the gravitational mass in blue is physically separate from the baryonic mass in pink. It proved dark matter is a real, separate substance. It moved the entire discussion from a compelling hypothesis to an established fact.
Okay, so now we know dark matter is a gravitational fact. The next monumental step is figuring out what it's made of. The astronomy tells us what it does, but particle physics has to tell us what it is.
Right, and we know a few key things it has to be. First, it has to be stable. If it decayed quickly, it wouldn't still be making up 27% of the universe billions of years later. Second, it must be neutral, with no electric charge. If it had a charge, it would interact with light and would have slowed down the bullet cluster collision.
And it mostly just interacts through gravity.
Exactly. And importantly, we know it can't be made of the normal stuffed protons and neutrons. There was an early idea about MACHOs, massive astrophysical compact halo objects.
Things like rogue planets, brown dwarfs, cold dust clouds, stuff made of normal matter that just doesn't shine.
Yeah, but we ruled those out. Microlensing surveys, which look for starlight being temporarily magnified when a dark object passes in front, would have detected them in huge numbers if they made up the halo. They didn't. They contribute only a tiny fraction, so we're left looking for a new non-baryonic particle.
And when we talk about how this stuff behaves on a cosmic scale, the consensus model is cold dark matter. What does cold mean in this context? It's not about temperature, is it?
It's not about temperature. It's about speed. Cold means slow moving. Cosmologists ran these immense simulations of the early universe. If the dark matter particles were hot, meaning they moved close to the speed of light, their high energy would have smeared out all the tiny density fluctuations in the early cosmos. Structures would have formed way too late and been way too diffuse.
But with cold dark matter,
With cold dark matter, or CDM particles that are slow and have low momentum, those small density variations survive. They act as the seeds, or gravitational wells, for galaxies and galaxy clusters to form. The simulations with cold dark matter produce a cosmic web structure that looks exactly like what we observe in reality.
so that narrows the field of candidates. Which brings us to the hunt for the actual particle. What has been the historically favored candidate for decades?
That would have to be the WIM, the weakly interacting massive particle.
It checks all the boxes. It's heavy, so it's massive. It's slow, so it's cold. And it only interacts via gravity and the weak nuclear force, weakly interacting.
Right. And the theoretical preference for WIMPs comes from this remarkable coincidence called the Wink miracle. Based on calculations from the Standard Model and extensions like supersymmetry, if a particle existed with a mass about 100 times that of a proton, and it interacted with the strength of the weak force, it would have naturally frozen out of the early universe at just the right rate to produce the exact amount of dark matter we see today.
Wow, so it just naturally falls out of the physics we already kind of know. That's a powerful motivation. Now, if WIMPs barely interact, how do you even look for them? I know there's indirect detection.
Indirect detection means you look for the aftermath when WIMPs destroy each other. If WIMPs are their own antiparticle, then when two of them collide in a dense area like the center of the Milky Way, they should annihilate each other. This annihilation would release a burst of high-energy gamma rays, so telescopes like NASA's Fermi Gamma Ray Space Telescope are constantly scanning the sky looking for an excess of gamma rays that match that signature.
Okay, moving to the second major candidate. This one is a whole different beast, born out of a deep theoretical need to explain why we exist at all. The axion.
The axion is completely different, yes. It's an extremely low-mass, low-energy particle, but it still counts as cold dark matter because it's produced with very low momentum in the early universe, so it clumps together easily.
And it was invented to solve something called the strong CP problem. What's the
Yeah.
simple takeaway there?
The simple takeaway is that, according to our theories, the strong nuclear force should violate a certain symmetry in a way that would have caused matter and antimatter to annihilate each other perfectly right after the Big Bang. The universe would have been left with just energy, no stars, no us. The fact that we exist means something is preventing that from happening. The axion was proposed in 1977 as a new particle field that naturally solves this problem. And if it exists in huge numbers, it could also be dark matter.
So it's very elegant. It solves two major problems with one particle. How do you hunt for something so incredibly light?
The strategy is totally different. You look for its interaction with strong magnetic fields. Axions are theorized to be able to convert into a photon when they pass through a magnetic field. So experiments like ADMX use these gigantic, super-cooled resonant cavities inside powerful magnets. They're basically trying to listen for the faint radio wave or X-ray that would signal an axion converting into a photon as it passes through. It's an incredibly difficult search.
And finally, a candidate that isn't a new particle at all, but one of the oldest objects in the cosmos. Primordial black holes, or PBHs.
PBHs are fascinating. They're not formed from dead stars. They would have formed in the first fractions of a second after the Big Bang from tiny regions that were just slightly denser than average and collapsed under their own gravity.
And they could come in a huge range of sizes, right?
From the mass of an asteroid up to 100,000 times the mass of the Sun. Stephen Hawking theorized that if these things formed from normal matter right at the start, they would have just become these non-luminous objects spread throughout the cosmos, acting as dark matter.
And the search for these is mostly astronomical, not in underground labs.
Mostly, yes. For the smaller ones, you look for their evaporation via Hawking radiation with gamma ray telescopes. For the bigger ones, microlensing surveys put strong limits on how many can be out there. There's been some renewed interest since LIGO started detecting merging black holes, because it's still possible some of those could be primordial.
So we've established dark matter as the gravitational scaffold of the universe. But now astronomers are pushing a new idea, that dark matter wasn't just passive. It may have been an active energy source that powered the very first stars.
This is a radical shift in perspective, and it's a genuinely new frontier being driven by the incredible power of the James Webb Space Telescope, JWST. The concept is the supermassive dark star.
And we're talking about the epoch of reionization, right? That period, a few 100 million years after the Big Bang, when the universe went from a dark fog to the transparent, star-filled cosmos we see today.
Exactly. These supermassive dark stars, or SMDS, are theorized to have formed in that early era inside those dense pockets of dark matter, the halos, that were the first structures to collapse in the universe.
And the power source is the revolutionary part. It's not fusion, it's WIMPs.
That's the core idea first proposed back in 2008. The theory is that a small fraction of the WIMPs trapped in that halo would sink to the center of the primordial gas cloud. There, the density of WIMPs would get high enough that they would start to annihilate each other, releasing enormous amounts of energy and heat.
So this heat, generated by dark matter annihilation, would actually hold the star up against its own gravity?
Precisely. It acts like a stable internal furnace. So instead of a dense fusion-powered core like our Sun, you get this enormous, puffy cloud of hydrogen and helium held up by invisible heat from dark matter.
How large are we talking?
They would be absolute behemoths, up to 1 million times the mass of the sun and millions of times brighter. If they existed, they would represent a completely different type of star in the early universe, one powered entirely by particle physics.
So why is this idea suddenly gaining so much traction now? What has JWST seen that these dark stars might explain?
Well, JWST is challenging our models in two big ways.
Yeah.
First, it's finding these unexpectedly bright, massive galaxies at extreme distances. They seem too big to have formed so quickly through standard star formation. Second, it's finding supermassive black holes in the earliest quasars. The problem is they just shouldn't have had enough time to grow that big. Supermassive dark stars are already enormous, and they would naturally collapse into massive seed black holes, solving that time problem.
So dark matter didn't just provide the scaffolding, it might have provided the power to light up the first objects. And we actually have specific candidates now.
We do. The evidence is tantalizingly fresh. A recent study identified 4 extremely distant objects from JWST that look consistent with the dark star hypothesis. The most compelling one, JWST's V140, is seen as it was only 300 billion years after the Big Bang.
And did they find a specific signal, a smoking gun?
They found a potential smoking gun signature, yes. In the spectrum of one candidate, they found an absorption feature at 1640 angstroms. This specific dip is expected in a dark star's atmosphere because the intense heat from WIMP annihilation would ionize a lot of helium. Finding that was highly suggestive.
But I understand subsequent observations of that same object have complicated the simple picture.
That's where the story gets nuanced and interesting. Later observations from the AOMA telescope found the distinct presence of oxygen in that same object. Now, to an astronomer, oxygen is a metal, anything heavier than hydrogen and helium. And the simple dark star model assumes they form in pristine metal-free clouds because they're supposed to be the first stars.
So the oxygen means other normal stars must have already lived and died nearby, polluting the gas.
Exactly. It complicates the pure isolated dark star model. The current thinking is that this might not be an isolated dark star. It could be a dark star embedded in a nebula that's already been enriched. Or maybe it's the result of a merger between a dark matter halo with a dark star and an early galaxy.
Either way, the possibility that dark matter was an energy source for the first lights in the universe has opened up a revolutionary new branch of cosmology. Okay, we have the overwhelming astronomical evidence. We have compelling candidates like the WIM. Now we pivot from searching the skies to the most challenging engineering feat in particle physics, the hands-on hunt for the physical particle itself.
This is the moment of truth. We're moving from gravitational inference to direct physical detection. We have to actually measure the scattering of a WIMP off a nucleus here on Earth. That's the only way to confirm what it is, its mass, and how it interacts.
And to do this, scientists have to create an environment so quiet, so isolated, it can register a single, tiny recoil event. Why are these detectors buried a mile underground?
It's all about creating an ultra-low background environment. Our planet is constantly bombarded by cosmic rays and other radiation from the rocks around us. Those would just swamp a sensitive detector. So by placing them nearly a mile underground, like at the Sanford Underground Research Facility in South Dakota, you use the Earth itself as a massive shield to filter out all that noise.
And every single piece of the detector has to be unbelievably clean.
Right, extraordinarily clean. Every component, the steel, the wiring, the water for shielding, has to be made from ultra-pure, low radioactivity materials. Even a tiny trace of uranium could create enough background radiation to ruin the experiment.
Let's deep dive into the flagship experiment leading this effort right now, LUX Zeppelin, or LZ.
LZ is one of the world's most sensitive WIMP detectors, built by a collaboration of 250 scientists. Its heart is a detector containing 10 tons of ultra-pure, ultra-cold liquid xenon.
Why xenon? What makes it so good for this?
Well, xenon is very dense, which increases the probability of a rare WIMP interaction. And as a noble gas, it scintillates beautifully, it gives off light, and it's easy to purify to extreme levels.
Okay, so walk us through it. A WIMP comes flying through the Earth, through the detector, and it finally hits a xenon nucleus. What happens? What does the detector actually see?
When a WIMP collides with a xenon nucleus, the nucleus recoils, and this deposits a tiny bit of energy. This recoil generates 2 simultaneous signals. First, you get a prompt flash of scintillation light, which we call S1. Second, the collision knocks off some electrons. Those electrons drift upwards into a layer of xenon gas, where a strong electric field accelerates them, causing a much bigger delayed pulse of light, which we call S2.
So S1 is the initial flash, S2 is like the electronic echo. And the key is being able to tell a WIMP hit from some other random particle.
Absolutely. The ratio of the S2 charge signal to the S1 light signal is the key. A nuclear recoil, which is what we expect from a WIMP, produces a different S2S1 ratio than an electronic recoil, which is what we get from background noise like gamma rays. This lets them very effectively separate the signal from the background and reject almost all the noise.
So what were the results from LZ's big first science run?
After analyzing 417 days of data, the LZ collaboration reported finding 0 confirmed WIMP events. Now, this non-detection is profoundly important. It allowed them to set new world-leading limits on how weakly a WIMP can interact, especially for lower mass WIMPs. These null results are really pushing the WIMP hypothesis into a corner. It means that if WIMPs exist, they must interact even more weakly than we thought, or maybe they have a different mass.
But the success of LZ has led to this fascinating new problem, an obstacle scientists are calling the neutrino fog.
This is a pivotal moment in the hunt. The detector is so good, so sensitive, that it's now picking up the irreducible background noise of the universe itself. The main background is no longer radiation from the lab, but neutrinos coming from the sun.
And the unavoidable problem is that these solar neutrinos interact in a way that looks exactly like a WIMP.
Exactly. They interact via a process called coherent elastic neutrino nucleus scattering, or CEVNS. The neutrino hits the entire nucleus, causing it to recoil. That nuclear recoil looks identical to the recoil we'd expect from a low-mass WIMP. LZ actually confirmed this interaction with high significance.
So the very thing that proves how sensitive the detector is, seeing these solar neutrinos, is also the thing that will fundamentally limit the search for dark matter in the future.
It creates the neutrino fog. For future experiments, this fog is an unavoidable background. It means distinguishing a real WIMP signal from a neutrino background becomes almost impossible, at least for low-mass WIMPs. The universe's own noise is now the biggest barrier.
If the basic interaction signal is so ambiguous, what other signatures can scientists look for to confirm a real discovery? They need something more than just a simple count of events.
There are two big ones, and they both rely on the Earth's movement through space. The first is annual modulation. Our solar system is orbiting the center of the Milky Way, flying through this vast, stationary halo of dark matter. As the Earth orbits the sun, our speed relative to that halo changes throughout the year.
Like driving a car in the rain, sometimes the front window gets hit more, sometimes less.
Exactly. We expect the maximum number of WIMP interactions around June 2nd, when the Earth's orbital speed adds to the sun's speed. And the minimum should be 6 months later, in December.
It's been a very controversial claim in the past, right?
Extremely. The DAMA experiment in Italy has claimed for years to see a highly significant annual modulation that matches this phase. But much more sensitive detectors like LZ and Xenon see absolutely nothing. This strong tension suggests the DAMA signal was very likely caused by some seasonal background effect in their detector, not dark matter.
Okay, so what's the ultimate confirmation, the real smoking gun?
That would be directionality. Because we're moving through the halo, the WIMPs should appear to be coming from a preferred direction on the sky, from the Cygnus constellation. If a detector could actually measure the direction of the recoiling nucleus and show they were all coming from Cygnus, that would be the ultimate unambiguous proof.
But that sounds incredibly hard to do in a dense liquid like xenon.
It is. The recoil track is microscopically short, less than 100 nanometers. You can't resolve that. So directional detectors use a different approach. They use very low-pressure gases. This makes the recoil track much longer, on the order of millimeters, so it can be measured. The trade-off is that gas is much less dense, so you don't have enough mass for high sensitivity yet. But it's the gold standard for confirmation.
Let's quickly survey the other technologies out there. We've talked about the liquid noble gas detectors like LZ. Their strength is scalability and that great background discrimination.
Right. They're the best for searching for high-mass WIMPs because you can build them really big.
Then you have the cryogenic bolometers, which operate near absolute zero.
Experiments like CDMS and CREST. They operate at incredibly cold temperatures, so they can detect the tiniest deposit of energy as heat or phonons. Their big advantage is an extremely low energy threshold. This makes them the most powerful technology for searching for the very lowest mass WIMPs, a range where other detectors lose sensitivity.
And finally, a really interesting technology, superheated fluids, or bubble chambers.
Right, like the Baikaio experiment. They use a fluid kept just below its boiling point. When a particle interacts, it deposits enough energy to nucleate a tiny bubble. The genius here is that they are naturally insensitive to most common backgrounds, like gamma rays, which don't deposit enough energy to create a bubble. And their targets often contain fluorine, which makes them highly sensitive to a specific type of interaction, spin-dependent interactions, giving them the world's best limits in that particular search channel.
Okay, so let's synthesize this. Where are we now in the hunt for dark matter? We have this overwhelming, indisputable astronomical evidence that it's real, that is the gravitational backbone of our universe.
It's a fact. The existence of cold dark matter is required to build the cosmos we see. And yet, the search for the particle itself, despite decades of the most sensitive experiments ever built, remains a frustrating null result.
No confirmed detections of WIMPs, axions, or anything else.
Right. And the null results from these huge experiments like LZ are drastically shrinking the available space for the traditional WIMP model to hide in. It also means we're pretty much ruling out those earlier tantalizing hints of signals from experiments like Dama. The consensus is that those were likely just misidentified background noise.
So, if WIMPs exist, they must be hiding in a very small corner. What happens next? LZ and the other big experiments are nearing the end of their runs.
Well, future collaborations are already being planned. The next generation, like the proposed Darwin detector, will aim for target masses 4 times that of LZ, pushing sensitivity down to almost unimaginable levels. The hope is to find that one elusive signal through sheer brute force, more mass, more time.
But the shadow of the neutrino fog looms over everything. That fundamental limit set by nature itself.
It is the ultimate challenge. We've become so sensitive that we've run headfirst into an unavoidable background of solar neutrinos for low-mass WIMPs, and eventually atmospheric neutrinos for high-mass ones. This natural noise floor means any future discovery has to happen before we're completely swamped by that fog.
Or it has to rely on those more complex signatures, like directionality, to pull a clear signal out of the noise.
That's the challenge.
Yeah.
It forces us to consider 2 paths. Either we find the WIMP very soon, or maybe the universe is telling us that dark matter isn't a WIMP at all, and that's pushing the community to invest more in searching for alternatives, like axions.
The journey from Zwicky's dismissed idea to building detectors that can tell the difference between a WIMP and a solar neutrino is just one of humanity's greatest scientific quests. We've established dark matter as a fact. Now we just have to find out what it is.
And we are now finding evidence, through things like the supermassive dark stars, that it may have played this critical active role in lighting up the cosmos right after the Big Bang, which raises an important question for you, the listener, to think about. If dark matter is so fundamental to creation, shaping galaxies and maybe even powering the first stars, what unforeseen subtle role might this invisible dominant substance be playing in cosmic evolution right now? Could it be influencing things we haven't even thought to look for yet?
Something profound to consider the next time you look up at that brilliant but tiny 5% slice of the cosmos. Thanks for joining us for the deep dive.